Hello, everyone. I want to thank everyone for coming and thank everyone in the grasp community for the warm welcome. I really enjoy talking to each of you, and I learned a lot from today's slides. Yeah. So the talk today is scalable sim-to-real learning for general purpose humanoid skills. I'm going to talk about several of my prior works, and I put it also I want to will explore two future directions that I found interesting about sim-to-real for humanoids. Sorry.
Can give you click once on your screen, you should be able to.
Okay, cool. Nice one. Yeah. So humanoid training is coming, right? I guess it's partly because of Elon and Jensen, but also we are now seeing these amazing humanoid lineups from companies like Figure, Boston Dynamics, 1X, etc. And today's talk's focus is that I want to explore how scalable sim-to-real learning could help for humanoids. There are going to be four aspects. First, control. Second is perception. Third is interaction. And fourth is evaluation. For the first part, I'm going to talk about four of my prior works, starting with human to humanoid, Omni H2O, hover, and aligning simulation and real-world physics ASAP. These all four works are learning from large-scale human motion data, and how can we do better systematic sim-to-real for humanoids controls. The second aspect, I'm going to cover two works. One is called Agile but Safe, ABS. This explores how can we use sim-to-real for high-speed, rapid collision avoidance locomotion. And the second work is called PDC. This is a pure simulation work. And we're going to explore how large-scale simulation could enable us to do RGB-based visual RL to do whole body manipulation. The third aspect we're going to cover is interaction. Aside from Omni H2 and PDC, I'm also going to cover two more works called Falcon, one on forceful adaptive control, and Wakoko, learning humanoid whole body control from sequential contacts. That's the prior works part. And for the future works, I will talk about one direction is visual sim-to-real at scale for humanoid local manipulation. And the second aspect is how can we use simulation as a very useful tool to evaluate real-world manipulation policies. And I put all of my prior works onto this three-axis spectrum. It has three axes. The first one is realism, whether this method could be transferred to the real world. I have some works that could only work in simulation. Some works could be transferred via zero-shot sim-to-real. And some work is really trying to push the boundaries of sim-to-real limits. The second work is called complexity. Here, what I mean by complexity is the number of dots you are trying to control for your robotic system. The basic is called whole body control. You are just controlling the motors between each rigid body links. The second is visual whole body control. You have perception, not only from proprioception, but you need perception to do, let's say, collision avoidance. The third aspect is visual whole body dexterity. With whole body control, with perception, we also want to add fingers. We also want to make the policy have manipulation skills. That's the complexity axis. The third axis is task diversity. Here, some of my works are trying to only learn a policy to do one single task. Let's say jumping, walking, let's say running, etc. And some of my works are trying to really have one policy for all kind of different motions. So putting things all together, here you see the three axes I'm going to cover about for today's work. And hopefully by the end of this talk, I want to share some of my thoughts on how can we get the purple point, which is trying to push the limits of both realism. We want to make it work in the real world. And visual whole body dexterity. We want to have perception, have whole body control, have manipulation skills. And how can we enable it to do as many tasks as possible? All right. The first part is control. Four works that we're going to cover. This first work is called human to humanoid. I call it H2O. So on the H2O is on this point of the axis. It can transfer to the real world. And it can do somewhere between single task and diverse tasks. and it only control whole body motors. There's no perception. There's only proprioception, and there's no dexterity. Here is H2O. So what is H2O? So the story began when I was 12 years old, and this is me 12-year-old. And there's a movie coming out called Real Steer. The movie is about like 20 years from now, we're gonna have humanoids fighting each other, teleoperated by humans. And there could be some sports league, and we are gonna enjoy the way we enjoy UFC as of today. And then my advisor Guanya bought a humanoid in 2023. I was his first PhD, and we both arrived CMU at the same time. He told me he bought a humanoid. Okay, I was like, at the very first impression, I told him I want to do real steer. I want to do teleoperation. And then during that time, there's another PhD at CMU called Zen. Zen works on physics-based animation, and he has done a line of amazing works on animation humanoid control. So putting all these three ingredients together, we have this. So this is the day me and Zen and Wenli, we unboxed Unitree H1 on January 2024. We're so happy, and we are so excited about doing humanoid research, not knowing how much suffering we're gonna have for the research. Okay, so you can tell when Zen is there, the goal is to enable something like this. This is Zen doing, there's RGB camera on Zen. He's doing movements in his office, and this is real-time post-estimation and then doing teleoperation, but only in simulation. The research question here we are trying to answer is, how can we make this happen in the real world? Before we go into the challenges we are gonna tackle, I wanna first answer two questions. The first question is, why do we wanna do this on real hardware? And the second question is, why is it challenging 2 years ago? The first question is, why do we want to do it, right? You can work in simulation. Why not? Why we want to put all these efforts to make it work in the real world? So this question dates back to the landscape of imitation learning 2 years ago. Back then, there are two amazing works coming out. One is called Mobile Aloha, building on top of Aloha's action chunking transformer. And the second is diffusion policy. So these two works really set the tone of how can we enable autonomous good robotic manipulation policy out of teleoperation. But you can tell this only works on bimanual arms, and this works on a single arm manipulator. So how can we teleoperate a high degrees of freedom humanoid? The recipe is still unknown 2 years ago. Because if you want to teleoperate a humanoid, the humanoid has to balance itself. And the very first control step is not clear 2 years ago. That's a unique challenge when you teleoperate a system like humanoid than when you teleoperate a system like single arm manipulator. So why is it challenging 2 years ago? The landscape of humanoid control 2 years ago is like, yeah, RL is making progress. Starting from quadruped locomotion at ETH's RSL lab, they are making amazing progress on their quadruped called Animal. And RL is also showing progress on biped robots. This is from Berkeley. I think Zhongyu has done amazing work on making Cassie running at Berkeley with our reinforcement learning. But back then, humanoid whole body control, state of the art, and no one is close to that, is Boston Dynamics and PC stack. So I put this RL, whole body control, and humanoid in red. My point is, 2 years ago, the RL for humanoid whole body control, the recipe is still unknown. So we're seeing RL making amazing and promising progress, but on quadruped and biped wrong only. For humanoid whole body control, no one knows how BD leverage their NPC stack. So we want to use RL, but for humanoid whole body control. We quickly identify 3 gaps. There are 3 gaps we want to tackle in this research. The first is infeasible motions. Because you can tell, even though Zen is not very athletical, but there are still some motions that he can do that a humanoid cannot. This is due to the hardware limits. This is due to the humanoid we can manufacture 2 years ago. And the second gap is, of course, sim-to-real gap. What you can work in an Isaac gym, the training and evaluation environment is the same, but we want to transfer it to the real world which means the training is on one dynamic system. The evaluation is done on the other. And third is that we really want to enable real-time teleoperation. Instead of pre-computing an offline trajectory to track, we want the policy to be responsive and reactive enough to track real-time motions. How do we solve it? The step one is we want to create a large-scale humanoid feasible motion dataset. We start with a humanoid motion dataset called AMOS. This is a mocap human motion dataset that contains more than 10K episodes of human motions. It's pretty large, walking, jumping, everything. But how can we turn that human motion into humanoid motion? Does direct inverse kinematics retargeting work? No, because even though humanoid is the most morphology-wise close to humanoid human body form, there's still quite a large embodiment gap. For example, Unitary H1 back then we're dealing with has a very wide hip. So the hip range between Unitary H1 humanoids is the twice distance between human hip range. So we first do a shape fitting process. Every motion in the AMOS dataset is captured by a human model called SMPL. And SMPL has several parameters. And we tune these parameters to make the SMPL human model better match the humanoid morphology. Then after that, we do a gradient-based retargeting. We have humanoid motion. So here you're seeing standard SMPL motion. In the middle, you're seeing the SMPL motion after shape fitting to better match the Unitary H1. The third, it might be not clear here because H1 is black, but you are seeing a humanoid Unitary H1 doing the same motion. Here's how the data pipeline works. But this does not answer the infeasible motion question. We are retargeting every motion in a data set to humanoid motion. So what we did instead is that we have a physics-based retargeting. We train what Zen has trained in the animation stack called PHC policy to track the full body. We have some success matrix on it. If the perfect RL, the privileged RL fails, we call it infeasible motions for the humanoid embodiment. Then we have a large-scale humanoid feasible motion that filtering out impossible motions. The second step is RL. So we have the motion. We define it as a motion goal for the RL, but also we define reward for the RL to track those motions. And we have 8 key points. So the reference motion we feed forward to the RL policy is shoulder, elbow, hands, and ankles, in total 8 points. And the policy only use realistic robot states. What I mean by realistic is that the policy only use the sensor information you can get on the real hardware, nothing else, because you can get a lot of, let's say, linear velocity of every robot rigid body links in simulation, but that's not feasible in the real world. And we have domain randomization to increase the robustness to enable sim to real. And finally, we do real-time teleoperation. This is me, and this is humanoid. Well, now here in this, we use an RGB camera to shoot our motion, and we have a real-time post-estimation module running behind to extract the human body kinematics information. We use hybrid IK here, and then we extract 8 key points for the RL policy, taking also proprioception to output the motor control of all the humanoid motors. This is what we enable. That's it for H2O. You can tell it has 4 limitations. The first is everything I do, the humanoid probably has a 200 or 300 milliseconds of delay of copying what I do. The second is that it still requires 8 key points, meaning that you need to have a pipeline that estimates the whole body movements of human. The third is the humanoid does not have hands. So it's just a bare elbow and a bare metal rich body link. There's no dexterity. And fourth is everything we showcase here for H2O is teleoperated. There's no autonomy at all. This leads to the second work I'm going to talk about called Omni H2O. This is a direct follow-up of H2O. On the 3-axis spectrum, it's still on this place, but we have added perception and interaction on top of the H2O pipeline. So what is Omni H2O? How can we solve the 4 limitations of H2O? First, instead of using the high latency RGB pipeline, because the first RGB cameras has latency. Second, when running a hybrid IK post-estimation module on another GPU, it also introduces latency. So here, instead of using this handcrafted solution, we use Apple Vision Pro. It gives you low latency, very accurate hand and finger post-estimation. The second improvement we did is that instead of tracking 8 key points of the human motion, we only track 3 key points. This is a trade-off. If you want to use Apple Vision Pro, it only gives you 3-point estimation. What I mean by 3-point is your head and 2 hands. And we have added dexterous sense on Unitary H1 robots. And finally, we have showcased autonomy empowered by imitation learning from the data set we teleoperated and also by foundation models like GPT. So there are 2 questions we aim to answer in this work. Number 1, why VR-based humanoid teleoperation is more challenging than full body-based? Second, how can we unlock autonomy out of VR teleoperation? So the first challenge is that you can see I plot the Google search 2024 January Apple Vision Pro available in the US. And the second month I bought Apple Vision Pro. And what VR-based teleoperation enables is low latency teleoperation, but it also only 3 blue points here are available compared to full body reference motion. This makes the RL training so much harder because the input is getting more sparse. Also, the reward is kind of becoming more with some ambiguity over there because you're only tracking 3 points. And how can you do full body control with only 3-point command? So here, what we do instead, we leverage a framework called teacher student. We first train a teacher policy that has every privilege information, both from proprioception, privilege proprioception, but also privilege motion goal. You can see I give basically everything I can give in simulation for the teacher policy, and I give full body reference motion goal for the teacher policy. Then I distill the teacher policy into a student policy that only has very limited proprioception available in the real world and very limited motion goal, which means 3-point in the real world. In the first place, teacher policy is trained by reinforced learning. The second phase, the student policy is trained by Dagger, which means direct behavior cloning from teacher's policy, but with students roll out in a simulation. This is what we enable by training this 3-point student policy and deploy it in the real world. This is me wearing Apple Vision Pro doing boxing. And this is, we are trying to draw H2O. Okay, you got it. So the third is loco-manipulation, pushing the cart and placing, picking basket and placing on the basket cart. And the fourth one is still loco-manipulation, moving forward, backward, picking things up, placing things down. Okay, this is not the end goal, right? We are not here for humanoid for teleoperation. We want something that moves autonomously. On the left, you're seeing the first-person view of the humanoid being teleoperated. We collect several data. On the right, you're seeing we train a diffusion policy. We are doing behavior cloning over the data set we collect out of teleoperation. Here, to be noticed that we are not imitation on every motor control, but instead we are only doing imitation on motion goals. We are only doing imitation over what we as human provide to the control policy. We are not learning from scratch we are not learning how the humanoid should be balanced. The control layer is frozen. Okay, at that time, at the end of the project, OpenAI released GPT, and it just came out of nowhere. I just go to the openai.com. I give GPT for all these prompts. You are a humanoid, and this is what you see in front of you, and decide what you want to react. And this is a human trying to greet with you, and this is me trying to hug. And then it took 2 or 3 seconds of API call delay. It's doing pretty well. This is powered by GPT. Yeah. Okay, cool. This is also, I want to give you a sense of what the system design looks like, because back then, a year ago, there are no very good system integration out of Unitary. So we need to build a lot of things from scratch. This is the cables and the onboard compute and powering behind the humanoid. We have 2 RNNX doing each compute payloads. We have 1 real sense on top of the head to record a first-person view of RGB, and we have 1 Z mini camera on the pelvis to do visual odometry. Okay, with that being said, I want to give a summary of the H2O and Omni H2O work. There are basically only 2 steps here for the human to humanoid pipeline. The first step is we do motion retargeting, and we train a tracking policy in a simulation. The second step is we train a deployable policy that can be deployed in the real world. For the first part, the motion source can be very flexible. We use AMOS dataset that is a publicly available mocap dataset on the internet. You can also use videos, graphics, or some professional software like Maya. And for the second part, how you train a policy is also very flexible. Here we are training the whole body tracking policy, but some works at Stanford and Berkeley, they're also training, let's say, video-based or vision-based tracking policy. But here, the point is the 2 steps, both for the motion and policy, are very flexible. Okay. After H2O and Omni H2O, I immediately realized something. At that time, this is hover on the landscape. It somehow trade off a little bit simulator capability. But here for hover, we are trying to really push the limits of diverse tasks. We are trying to make 1 policy to do as many things as possible to make it versatile. Okay, so just 6 months after H2O, and things are moving so fast. Works coming out from Stanford and UCSD. Everyone is now, back then, a year ago, is doing reinforcement learning, training from human motion and whole body control on humanoids. But if you take a step back, what is different is that even though they are all doing RL from human motion, the command space is very different. Some works use command for the lower body velocity tracking and upper body joint angle tracking. For H2O and Omni H2O, it's a reference kinematics motion tracking. So if you really look at humanoid, it's one of the most promising platforms for versatile robotic application, right? That means it can do a lot of things, ranging from navigation, manipulation, and loco-manipulation. For each task, it might need only a subset of the full command space. It could be root velocity, head position, upper body joint angle, or whole body joint angle positions. So the research question we aim to answer in the hover work is that can we really have a unified command space for all these different possible humanoid command space? So this leads to the hover work. The idea is very simple. We also train an oracle policy, a teacher policy that takes full privilege proprioception, tracks full body motion. But when we distill that into a student policy, we're not distilling only to a 3-point tracking policy, but instead we're randomly masking the command space for the student. Therefore, giving the student policy a robustness of tracking whatever the command that is not masked. So here, we're really trying to make 1 policy that works for all versatile control interface, ranging from VR, RGB, exoskeleton, robotic arms, mocap to joysticks. We really want you can control the same humanoid with the same policy by both keyboards, VR, and probably mocap suite. The way we do it is that we have this versatile multi-mode command space by masking out the command during distillation. Here you're seeing the same policy controlling the humanoid. Whatever you see is the command it has. Here is 1-point tracking, 8-point tracking, 3-point tracking. And here is the velocity tracking. You can see the arrow. So it's pretty versatile. No matter what you command, it can follow. And finally, after H2O, Omni H2O, and hover, you can see we're doing a lot of things on humanoid control. But really, we're just reproducing the success of quadruped synchrotron on humanoid. So here on ASAP, I trade off a little bit of task diversity. I want to simplify the task as simple as possible. I want to have one policy to do only one thing. Let's say Kobe Bryant's fadeaway jumping. But I really want to push the real world performance limits as far as possible. So this is ASAP, a work that only focus on how can we do better sim to real. So I guess everyone in this room has seen these amazing demos coming out from Unitree and Boston Dynamics. They are all powered by reinforcement learning. And this year at RSS Humanoid session, 9 out of 10 papers are doing reinforcement learning sim to real for humanoid control. So I can probably say that reinforcement learning is the go-to method for humanoid control at 2025. So how does sim to real work? For a lot of you who hasn't really touched on the first-hand experience, sim to real starts with largely parallelable simulation on GPU. And then we define the reward function, we cook the RL algorithm into it, and we have this transfer. But unfortunately, this kind of smooth transfer is not always the case. What you end up is more likely something like this. A policy that works perfectly in a simulation works terribly wrong in the real world. How can we solve this? Before ASAP, there are 2 go-to methods for sim to real. One is called domain randomization. The idea of domain randomization is, okay, we know our simulation dynamics models are wrong, but let's train on as many wrong models as possible to robustify our policy. The second method is called system identification. The idea between system ID is that, okay, our model is wrong. How can we find better simulation parameters to make our model better match the real world dynamics? If you take a closer look at both methods, you'll see the key here are models. So the research question we aim to answer in the ASAP work is, can we learn a correct model with reinforcement learning from real world experience? How can we do it? How can we learn a better model with reinforcement learning? It has 4 modules. I'll break it down to you. First, it starts with what we do in H2O, motion tracking. We train a policy that tracks human motion and we deploy in the real world. But the story does not end here, and it's just the beginning. We deploy in the real world, we collect real world data. Here is how the data pipeline works for pre-training. This is me doing Cristiano Ronaldo's jump at CMU. We do post-estimation on it, and you have SMPL motion. And then we do a RL tracking to clean the offset and to clean the motion we get from post-estimation. And then we do inverse kinematics retargeting. Then we have G1 motions, right? We train another RL to track the G1 motion. Finally, we deploy a policy in the real world, ranging from me doing it to a real G1 hardware doing the same thing. Second is that we deploy the policy here in the real world. I have mocap markers on the humanoid. Then I record every proprioception sensors and mocap in the real world. We have a state action pair trajectory that happens in the real world. Then I reset the simulation to the state where what we record in the real world by playing back the actions we actually execute in the real world. So the simulated states and real world states under the same actions, starting from the same initial state, are going to be different because of the dynamics drift. So here we define a delta action module. This is a RL network. It takes state and the action you're gonna take at this point and outputs a delta action before the action actually goes into the simulator. The reward for this delta action model is the difference between the simulated states and real world states under the same action rollout. After training the delta action, we have a kind of a hybrid simulator. The simulator consists of a rule-based traditional simulator plus a neural network that transform your action you're gonna take with a delta action to make the simulator plus delta action module behave more like real-world dynamics. And then we fine-tune the policy in this hybrid simulator. Here, we are trying to, my hope is the hybrid simulator will behave more like real world. And finally, we deploy the policy in the real world without any delta action module because the real world does not need to be compensated for. Okay, here's the roadmap of this framework. On the left, you're seeing the policy we get from pre-training doing a kick motion. And on the right is the policy we get after collecting the data of this kick motion, and we train a delta action module Then we fine-tune the policy on the hybrid simulator. Finally, we deploy in the real world. The policy gets more smoothness and better elegance during the same motion. And here we plot the magnitude that delta action model actually learns during this real world feedback. Here, larger the red dots are, larger the magnitude of the delta action is. So you can get a sense of what the delta action model actually learns. The biggest delta action model come from knees and ankles. This is where the delta action, reinforced learning delta action model believes the most sim-to-real gap comes from. Here is the control part. We're moving to the next part, perception. For the first work is ABS. Here, we're trying to answer how can we make our robots from simulation to the real world, but when they are deploying in the real world, they are not blind, because everything I present, H2O, Omni-H2O, hardware, and ASAP, all the control policy are not perceptive. They are blind policy happening in the real world. So here, on the axis, ABS could transfer to the real world. It can do a lot of locomotion tasks, I would say not many. And then it has visual input. It has depth sensing camera doing whole body control for quadruped. The research question we aim to answer in this ABS work is that, number one, how can we scale up safety from sim to real? Second is that, how can we learn depth-based perception for sim to real? So for the first pipeline, we train an agile policy here. This is a reinforced learning policy, and we have a safety layer on top of it. We have a reach avoid value networks that we learned from simulation rollouts. This comes from control theory, reachability analysis, and it gives you a sense of if the value is above 0, you are going to crash no matter what you did. And if the value is below 0, you have something, there's a possibility for you to stay safe. So here, by leveraging this network, we define a threshold here. If it goes above the threshold, we activate a recovery policy that only optimizes for safety. And it is below that, we use agile policy to reach goal. That's number one part. That's number one for safety. Number two is to make it really transferable in the real world, in the wild, with onboard compute. We want to make it have perception. So here, what we did is that we have 8 assets importing in a simulation, and we render depth image out of it. So we have a pair of data set. This is what the quadruped is going to see in front of it. And this is the distance between quadruped to the obstacle. We have a ray prediction network, taking depth image as input and predicting a 11-dimensional ray distance, like a LiDAR, but coming from depth image. And I got a question of why depth image instead of LiDAR? Because here, back then, even as of today, the LiDAR you're gonna get on the market could only give you 10 hertz, 20 hertz at maximum. But if we are pushing the agility limit, if our quadruped is running really fast, let's say 3 meter per second, that 10 hertz delay means 30 centimeter delay. So that's crucial for collision avoidance. That's why we want to enable higher frequency sensing sensors like depth camera. This is how we transfer the depth image to the real world by adding a lot of, let's say, horizontal flip, random erase, Gaussian blur, and noise. The second work I'm going to present is PDC. PDC happens here. It's a simulation-only framework. It can do a good amount of loco-manipulation tasks, but it has visual whole body dexterity. That's what I'm most excited about. So in PDC, we created a bunch of kitchen scenes and mostly kitchen scenes. And we have a RGB perception, taking after CNN, NLP, and GRU, and controlling the whole body, all the way from whole body motors to every finger motors to do local manipulation tasks in the simulation. And there's no distillation happening here. Everything is visual RL. This is, I think we scale it up on tens of hundreds of GPUs to make it really work for visual RL training. Here, the humanoid also has active perception. We are observing an emergent search and found behavior by visual RL. When we have the command of, let's say, put this thing on that table, if the current RGB view cannot observe that object, RL learns to search for it. Okay, I'll skip the emergent behavior part. And finally, I want to present two works that focuses on interaction. On the H2O, I have covered. We have interaction out of teleoperated dataset and imitation learning 8 module. And I want to first talk about a work called Rococo. Here, I also put Rococo here. It explores whole body control, but with another perspective. The research question we aim to answer in Rococo is that, okay, we know the recipe of doing humanoid control out of human motion prior, but can we really learn humanoid control without any prior, but with just sequential context commands, with sequential context planning? Here, everything you see here, the humanoid is commanded of there's a contact should happen here, and the whole body controller tracks it. More details I'll skip for this presentation due to the sake of time. Then the second work I want to present about interaction is called Falcon. Falcon is that really, when we are trying to make humanoid do any kind of heavy duty task, we want it to be, let's say, forceful, adapted enough to both control the whole body with payloads on it and without. So here we explore the structure of humanoid whole body control. We train two separate RL agents on it. One is controlling lower body and the other is controlling upper body. They are sharing the observation, but with different value function and rewards. Here, you're seeing the resulting control policy, putting a cart with two humanoids in it. It's very heavy cart. Here, the humanoid is booster T1. It's like roughly this height, but it can pull a cart with 85 kilograms. And here, this is Unitree G1 trying to open a heavy door at CMU campus. It looks heavier than I thought, because I thought at the very beginning when I see the video, I think it's okay. It's not that forceful interactive, but when I have a force sensor on it, it's really heavy. So the idea is that we train dual agent RL, two policy, two value functions to make it really work and efficient for forceful adaptive. Okay, so that's it for the prior works. Everything that I covered today is open source, all the way from simulation training, motion retargeting, and deployment. Okay, I also want to spend some time talk about several future directions that I'm interested about. Number one is visual sim to real at scale for humanoid local manipulation. You can tell that here today I spent a lot of efforts on control part. Sim to real for control works. No one doubts it. Second, sim to real for interaction, mostly dexterous manipulation. OpenAI did a work 7 years ago. And then there's follow-up works coming out of NVIDIA doing dexterous manipulation, pick and place with RGB and depth sensor input. And also for the perception community, there are a lot of works like foundation pose, doing 6D pose estimation with synthetic data. You can tell for all three aspects, control, perception, and interaction, sim to real works in some sense. But really, we are not able to pull up a demo with sim to real to do something that Boston Dynamics shows for their local manipulation task. I don't see really a blocker for this. Maybe computers, also hardware needs to be robust enough. But I'm really excited to see a work of combining control, perception, and interaction end-to-end with sim to real. The second work that I'm interested about, as foundation models are getting more and more complex, and we need to have better protocol for evaluation. This is not for ranking model A and model B, but this is really for you to iterate on it. Let's say you have a better action tokenizer you think of today, but how can we conclude that checkpoint A is better than checkpoint B? I think here, simulation could play a huge role here. I think real to sim evaluation is a dual problem of sim to real. If you can do very good sim to real, that also means your sim performance has a very high correspondence of the real world performance. That also means you can do very good simulation evaluation for your real world robotic policies. Okay, that's the two directions that I'm mostly excited about. finally, I want to take a step back. This here I put some snapshots of a paper 10 years ago, exactly 10 years ago from CMU. 10 years ago, there's a challenge called 2015 Humanoid DARPA Challenge, and there are several teams attending it. 10 years from after that, we now have better humanoids, we have better control policies. And I put three paragraphs of Chris Atkinson from CMU. He wrote in the paper. Number one is, after 2015 DARPA challenge, he said paradigm shift needed. I think this happened. We are now having way better hardware. We are now using QDD for humanoid motors instead of hydraulic humanoids. We are now using RL sim to real for control instead of MPC stack. Paradigm shift happened, but I think we still need more. Second is there's something wrong with robotics. This is very funny, but here Chris said that we need to understand why our current hardware and software approaches are so unreliable. I think this point is still true today. I think for the past year, I spent some time, the total amount of time I spent with Unitree G1 is 9 months in total. And in total, I've break three humanoids, total failure. I have to ship them back to Unitree. There's no way that I can repair them. Not to mention the small breaks that I can repair myself. The third point, Chris said that we can do better in terms of control. I think that's still true today. Even though Sim2Real RL is making amazing progress, we're still far from human agility. Let's put agility aside, we're still far from human's robustness, right? We have one control policy that do all the things. We do sports, we do daily local manipulation, right? Now we're still far from that goal. Okay, with that, I want to conclude here. I want to thank my PhD thesis committee, my sponsor, my collaborators, and all the robots that I spent late nights with. I'm sorry I break you many times.
We can open the floor for questions.
Yes, yes.
So great talk, thank you so much. And I want to ask a question about learning from human videos, because earlier this year, Tesla shared a video of them having some quite impressive local manipulation results. And they claim that this is learned only from human videos, whereas you motivated a lot of your work through using human to teleoperate the robot, not just using the video itself. So I was wondering if you, as the expert in this field, could you share some thoughts on these different kinds of approaches?
Yeah, so the difference here is that we are learning control here, right? But for Tesla, they're actually learning manipulation. So they are not trying to learn from human video to teach their humanoid how to balance itself. They are more or less learning a perceptive manipulation skill. So as for manipulation, I think both data sources matters a lot. Teleoperation data might be the best, right? But it's not that cost effective. For human video, we have a bunch of them on YouTube available, but probably most of them are data that are hard to leverage. So yeah, human video, I think, is a very promising method of scaling up data for robotics, because if you think about the success of, let's say, GPT language models, every word we type on the internet is human data, right? But there's no embodiment gap between human using language and the GPT using language, but there is for robotic systems. Yeah. Yes.
Thank you for the talk. I have a question about the delta action module in
Yes.
the SAP paper. I think the motivation of this part is you want to correct the simulation prediction or the simulation rollout to align them with the real world. But I mean, you could use many ways to do so. I mean, you could train another network to predict the residual to the simulation and just simulation add that part and then equals the real world. So what is the insight to tune the action instead of other parts of this simulator?
Very good point. So why are we learning delta action instead of delta state, right? So actually we have a delta state baseline in the paper, but I would say more intuitively, the way I understand why delta action works better is that it has the smoothness guarantee. Because whatever you output as delta action, it has a layer after that. We call it simulator, right? But simulator is just numerical optimization. That smoothness between state to state transition is guaranteed by numerical optimization. But if you're learning a delta state, by just adding that delta state on top of the state that simulator gives you, the manifold of the state distribution you not get might be less smooth when you do delta action. I think that's one potential reason that I feel like why delta action works better.
Okay.
Yeah. Yes.
Okay. Thank you for your comment, first of all. I guess I'm curious, like, to your last area of like unreliable robotics, I noticed there seems to be a through theme of you learn a policy and you have a correction factor to it. So you have like your agile control network, and then you have your correction factor. Your sort of learned policy, and then your delta correction network. I'm curious, do you think that this line of like take action and then correct for it will be sufficient to make your maybe systems a lot more robust, or is there something that's fundamentally missing from like action correction?
Yes. For the safety part, the action correction is really we want to have something that gives you more confidence that the system is safe. That's why we need something that as a backup plan. And for the ASAP project, it's not really correcting the action, but more or less correcting the simulator, but in the form of action, aligning the dynamics. So your question is the way to go for future development? Or like,
you mentioned sort of this notion of making our simulators more robust.
Yes.
And then there's this other through line of like unreliable hardware and software approaches.
Yes.
Do you think that sort of correcting for those via a like second correction step is the way to go, or is it just like learning end to end, trying to have like well-aligned dynamics to begin with?
Okay. I feel like both not. I can share a experience from me doing humanoids in Tairan. At the very beginning, we have Unitary H1, right? I spent almost like 1 or 2 months to make the RO policy control Unitary H1 to be able to stand still and stably locomotion, do stably locomotion. I spent 6 weeks, around 6 weeks. And the day I received Unitary G1, I make it work in 4 hours. Of course, I'm getting better at it, but it's more hardware are improving. Hardware are getting more and more sim-to-real friendly. So I guess the fundamental solution here is better hardware. Yeah. Yes.
So great talk, by the way, but so going off of that, what sort of dimension of hardware improvement do you think is most needed, or what do you find most lacking? You mentioned that 6 week or 4 hour, iteration. What caused that?
Number one, Unitary G1 is smaller and lighter, right? Number two is, I don't know what Unitary engineers did, but they definitely did a great job in terms of torque transparency. What I mean by torque transparency is that now we're doing quasi-direct drive motors, which means the gear ratio is low, but there's still some gear ratios over there, let's say 15 for Unitary motors. Better torque transparency means when you output the motor, when you command the motor with a desired joint angle, the torque you actually get out from this hardware is matching what you expected, right? So I think that's one of the biggest advantage of quasi-direct drive motors, that you have better torque transparency, which leads to more sim-to-real friendly. And you're asking about what else do I expect? I think I expect one thing, just don't, I want a robot that don't break, right? I guess there's still a lot of work that can be done there. Yeah. Yes.
First of all, thank you for the talk. It was amazing, very interesting. I want to ask, earlier on, you said that much of the big discrepancy you found between the human body and humanoid body after you made the adjustments for scale was the motors in the ankles and in the knees. Found that they were very erroneous when you're trying to apply it into the real world.
Yes.
Do you think that's because of the robot having to do a lot of dynamic motions with a big load that needs to be supported by these leg motors? Or do you think it comes from a different source that it's not related to the high workload legs?
It's really not. I feel like it's just Unity's first humanoid. So the design is not good enough. They are trying to make the most conservative design in terms of hardware. You can see how wide these two legs are. It's right. This is their default motion, around half meter wide. Yeah.
Okay.
Yeah, I think they're doing better job on G1 already, right? Yeah. Yes.
I have a question. So I think it's important for robot to move, but also important for robot to actually do stuff for
Yes.
us. So in terms of manipulation, there can be many different variations, including like spatial variation, color variation, or even task variation, instance variation.
Yes.
So how do you think? Do you think it's enough data to be the cure to it, or do you think there might be missing piece here in terms of like general?
If it's really enough data, I think it'll solve it.
Oh,
Right?
Yeah.
You already said enough.
yeah.
Enough means solving it,
Yeah.
right? Yeah. I think data is the way to go as of today, right? I think the way I understand this is think about how we do sim to real. Doing sim to real, we really need very good grad school students, right? Who understand Python, who understand simulator, who understand reinforcement learning, and who understand deployment. These kind of grad students are not that many on this earth. For them to inject their priors to make robotic system works, probably you will get some of the graduate student doing it. But if you think about using data or using, let's say, teleoperation to teleoperation manipulation, basically everyone can do it, right? It has no entry barrier point for you to understand Python to teleoperate a humanoid, right? I think they are getting another way more magnitude of human prior for manipulation if you are doing teleoperation instead of sim to real.
Yeah.
Yeah. Yes.
May we go back to the PDC?
Yes.
Okay, so I'm quite curious, what is this motion plywood is? Is it something this black box factorized as a motion plywood, or there's a plain non-real definition?
Yeah, motion prior is a work called Pulse, Pulse, from Zen. So what he did is that we have motion tracking policy, right? He distilled it into a VAE. So instead of directly outputting the reference motion, you can directly output a latent space to leverage the motor priors again. Yeah. Zen's amazing. Zen's works are amazing. Check out his works on animation. It's really good PHC Pulse stuff. Yeah. Yes.
So you mentioned that there's a huge gap between independently for Unity, the G1 and FX pretty much. So, and also you said future work we should do more innovation. Since that all those humanoids companies, there are so many like evolving gap. How should we like do a fair comparison between each robot, or how should we make the inspiration actually useful for signal for next iteration?
Simulation. That's what I feel like the advantage of simulation. Because on day one you do Unity H1, on the other day you do Unity G1. There's no cost in simulation. But if you want to have an evaluation protocol for all possible policies, for all possible robotic systems, it's really hard to do them on hardware for every company, every grad school labs, and even for the same robotic arms. We're using different cameras, right? We're placing the camera on different places. Yeah, it's basically a free lunch in simulation because it's just a URDF change.
But the environment is very expensive. Like for example, in manipulation, how do you like construct work so you can have a benchmark?
I don't think we need an environment that simulates everything in this world. Maybe all we need is like, let's say 10 very high fidelity simulation tasks and environments. That could be, that there's a possibility that we can construct a high correspondence between those 10 tasks and more tasks, right? Yes.
Actually, I have the question about simulation, like, so basically we're thinking like there's inevitable gap between scenario, right? What is the chance of like simulators like actually get much better like by leveraging, I don't know, AI or like using those data on the simulator to like have a more realistic environment and make simulator more viable? What's that possibility?
So the question is the possibility of simulators getting better.
Yeah.
As of today, I think we are not seeing really better simulator, but we are seeing faster simulator and more parallelable simulator. If you look at the underlying physics engine of Isaac, it's still physics, right? Physics has been here for quite a while. And the underlying how physics handles friction and contact, it's not accurate at all. It's just fast, right? So how can we make it more accurate? It trades off, it needs more computation for sure. And I think also maybe rule-based simulator has a ceiling on it. Maybe we need to make it more data-driven. That's an open question. Yes.
So the frameworks that you have shown throughout these works, it seems like there's a lot of different training modules that you go through. Were these portions modules found through experiments and you're like, oh, there's a gap here, so we need to create this delta module. And then we get to a certain level of performance and then you're like, okay, I need to do another module to scale that gap. Going through all these works, do you think you can skip a lot of these steps, or do you still find that you still need to go through this type of iteration?
I think we're going to get less and less iteration as the hardware getting better and better. That's why I feel like after ASAP project, the benefit of doing this kind of real-to-sim neural simulator stuff for QDD-driven humanoids is getting more and more marginal. Maybe for harmonic drive motors, maybe for soft robots, better neural real-to-sim could still make a huge impact. But as of today, better hardware, at least for humanoids, is a more cost-effective option to make the transition better. Yeah.
Last question from online. So you have all these policies for different tasks. Do you see a solution of mixture of experts of architecture doing something like this? And then another question is like, there's a difference between whole body locomotion and upper body manipulation, like those VLA based methods. Do you think there's a paradigm to combine them, or do you think there's separate is?
Okay, number one question is how we have different policy for different tasks. How can we make it, let's say, mixture of expert? I think it really comes down to the application we're trying to solve. You need to give me a task or scenario that we really want to push the efforts towards it. If there is one, I believe we're going to have a mixture of experts, for example. But here it's just research papers. So we just want to make sure we answer the research question. But from a practical view, yes, that's possible. Okay. And the second question is, okay, how can we combine this whole body control stuff with VLA? It's already happening, right? For the demos, as a figure shows, 1x shows, it's always combining a high level, no matter it's a VLA or let's say diffusion policy, is combining manipulation, semantic perceptive manipulation policy with underlying whole body control. Yeah, it's very intuitive combining these two. Yeah.
Great. Let's thank our speaker again.